All right, recording is rolling. It is Friday, February 10th. So we're going to continue with these chapter 12 questions from your guys' book. Okay. So I went ahead and printed these out from Excel. So my numbers are different than your numbers, just like yesterday. You guys have unique papers from each other too. And then on Monday, there's going to be a Navy presenter. So yeah, be good for the guests when they show up. And here we go. So yesterday we did a couple of these. We were looking at here, just recap those so far. We're saying how much energy would it take to heat up water to bring it to a boil? And this graph down here is really helpful. Okay, so how much heat energy going around this graph to take to go from room temperature to bring it just to a boil? That was number one. And number two says if you've got a waterfall at some height, what's the temperature change at the bottom? So it's kind of like a conservation of energy thought process. There's potential energy at the top. You could say there's kinetic right before it hits the lake below, and that's all we did last semester. But then when it bam crashes, where does all that energy go? Well, a lot of it's going to go into thermal, so it could raise the temperature a little bit. I think you should have got like a fraction of a degree Celsius, right? If you did it right, fraction of a degree Celsius. Okay. All right. So MGH turned into MC delta T. All right, pretty much. Okay. All right, number 55. We got a 50-gram piece of mystery metal. Yeah, my number's different than yours, but so mystery metal at 100 degrees Celsius, placed in 200 grams of water at 20 degrees Celsius, and the mixture reaches equilibrium at 22 degrees Celsius. What is the specific heat of the mystery metal? And once you figure out the answer to this question, what you can probably do is pull up a table of values and say, oh, well, that must be like aluminum or zinc or whatever it matches, right? If it, assuming it's some constant material. Okay. And so, see, 50 grams of metal, 200 grams of water. Now, already it's a kind of I mean, there's more water than metal, but it's not crazy much more. It's like a 4-to-1 ratio. You see that? Okay. I'm trying to get a big picture before I start like jotting down equations and doing numbers and stuff. Okay. So, do you guys notice that the metal was crazy hot and the water was basically like cool room temperature, the cool side of room temperature? Is that okay? And then you mix it all together, and what happens to the final temperature? You guys see how the water temperature only goes up a little bit? It's like a couple of degrees. And wouldn't it be true that at the same time, the temperature of the metal would plummet down to match that temperature, hence equilibrium temperature, right? So the big picture point that I'm trying to make here, it has to do with specific heat capacity. Remember, I've been telling you guys last couple of days that it's really hard to change the temperature of water. Water has a huge specific heat capacity. Okay? It takes a lot of energy to heat it up, takes a lot of energy subtracting to cool it down. So the temperature of water is relatively stable. All right. So here's the big picture idea. Now, how are we going to solve this? Number 55. Okay. Well, here, let's get a picture going. Water, mystery metal. Okay. Now, this mystery metal is like emanating heat energy. Maybe we can call it like delta Q. Right? And the water is importing that heat energy. Is that also true? Let's say this is an isolated closed system, so no energy is leaving or exiting this metal water system. Okay. Okay. The first law of thermodynamics says that energy is conserved. I can say like this: the heat energy lost by the metal is exactly picked up by the water. I might throw in a negative sign to talk about import export, right? The energy lost by one is gained by the other. You can actually put the negative sign in either side of the equation, and you'll get the same answer at the end. Okay. All right, is that all right? So that's the framework to solve this. Energy in equals energy out. Right? It's an exchange. Now for the metal, we're going to go mass of the metal, specific heat of the metal, times the change in temperature of the metal. And for the water, we're going to go mass of water, times specific heat of water, times the change in temperature of the water. And slap a negative sign somewhere there if you want to be really consistent about it, right? Import, export of heat energy. Right? Can I be sure? Right. No, neither of these are going to be changing phases. Right, the water was liquid before and still liquid. Metal was solid to solid. Right, that's why I don't have to worry about like on those graph cutting across any of these jaggedy legs or anything. So the water is just liquid within this part. Metal's just solid within this part. Okay, so that's it. Right, and they're headed toward each other, right? So the water and the metal the water heats up a little bit, the metal cools down a little bit, and it should like this, I guess I shoot. Okay, and we should have all these numbers except for the specific heat of the metal. Therefore, we can solve for that and figure out what metal it is, right? That be true? Okay. So yeah, now we can plug and chug, but you guys see the big picture, how this can work. So we got 50 grams of metal. Notice we're sticking in grams. Yesterday we did grams too, which we hardly ever do in this class, but I guess this week, right? Okay. We're solving for specific heat of the metal. And we're going to 22 degrees from 100 degrees Celsius, right? Now, whether you're working in Celsius or Kelvin, as long as you take a temperature difference, is it the same thing? Like if I converted to Kelvin first and I took the difference, would I get the exact same thing as taking the difference in Celsius? Yeah, it's the same thing. A change in 1 degree Celsius is the same thing as a change in 1 Kelvin. They're the same thing, right? Okay. I ran out of room. All right, I'm gonna start over. All right, 50 grams. Specific heat of the metal we're solving for. We're going to 22 degrees Celsius from 100 degrees Celsius. Okay, so I just copied pasted that part too. Okay, equals, and then the energy imported by the water. Mass of water, I have 200 grams of water. You guys know that water has a specific heat capacity of, and I wrote the number right here, 4.18 joules per gram Kelvin. 4.18 joules per gram Kelvin. Okay. The fact that this is grams and this is grams. Keep that in mind, because remember yesterday for the waterfall, you had to be careful. You had to do joules per kilogram Kelvin. This number was like 4,000 something. You guys remember that? So be careful to build that. And then the change temperature of the water. Well, the water ended up also at 22 degrees, but it from 20 degrees. So it only raised its temperature by 2 degrees Celsius, which is also a rise in 2 Kelvin. Okay. Temperature change is the same thing in either system. Right? Okay. So bet everybody can get it from now for sure. But let's see, what's 22 minus 100? 978 times 50. Okay. So C times negative 3,900 weird units is equal to what's 200 times 4.18 times 2. Okay. Negative 1672 like weird units. Okay. Okay. So you divide that down. I'm looking at a specific heat capacity of, I'm getting 0.429. Okay. And the unit, if I kept track of my units, would have to be joules per gram Kelvin. Okay, because this was joules per gram Kelvin. We're doing everything in grams. That'd be like that. Okay. You guys remember specific heat capacity of water is approximately 10 times that. Water is like 4.18. Metals are like 0.4 something, okay? So it's 10 times easier to change the temperature of metal compared to water. Okay, you put in the same amount of energy to each one, and water is really stable. And metals, their temperatures fluctuate crazy. Next one, 56. Zoom in here. 600 gram sample of water at 90 degrees Celsius. Okay, so that's really hot water. It's might get close to boiling. Right? It's mixed with 400 grams of water at 20 degrees Celsius, which is like room temperature. What's the final temperature of the mixture? Oh, I bet we could do a setup that's pretty similar to what we just did, except we're solving for something a little bit different. We're solving for the final temperature. Like last time we knew that the equilibrium was 22 degrees Celsius. That showed up on both sides. Right? Now we're going to know the specific heat capacity both because they're both water, water, and water. We're just mixing water and water. And we're going to solve for what is the final temperature. But otherwise, it's the same framework, isn't it? Right? Like that. So we're mixing, right, so number 56. We're mixing water together. And the delta Q lost by 1 mass of water is the negative delta Q, the water, the energy imported by the other water. This is the first law of thermodynamics again, just like the last question. Right. So I got mass of the water, one mass of water, maybe mass A, specific heat of water. Delta T is T final minus T initial, is equal to negative mass of water B, specific heat capacity of water, same, water is water. T final, same T final, just up there and there we're solving for, minus temperature initial mass B. Okay. Plug in some values. So my paper, I got 600 grams and 400 grams. So 600 grams here, 400 grams here. Throw in a negative sign, track it right. Import, export of energy. Oh, specific heat of water, you guys know is 4.18 joules per gram Kelvin. That's also true here, 4.18 joules per gram Kelvin. Now, but pause for a moment, because it's good to get a big picture of what's going on in terms of the physics variables. You guys remember last semester, sometimes things would cancel out. So it was oftentimes masses canceled out or gravity fields canceled out. Not all the time, but sometimes. In this case, you guys see that the fact that we're dealing with the same material, it could be any material. And the fact that it's the same C just cancels out anyway. So even if you didn't know that, it doesn't really matter. And then TEF we're solving for. Now 600 grams started at 90 degrees Celsius. And the 400 grams started at 20 degrees Celsius. Feel like that, right? Like that. Okay. Yeah, you could convert to Kelvin if you wanted to, but I don't think it really matters. Okay, so I'll just do it like this. I'll just like cross multiply them. It's distribute, I should say. Distribute, 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 distribute. Okay. This is just a math process at this point. There's probably different ways to go about this. So 600 TF, also drop my units just to make this look a little cleaner. 600 by 90, 54,000 equals negative 400 TF plus 400 by 20 is 8,000. Okay. Of course, there are units attached to all those numbers, and just do a little shortcut here. Okay. So add 400 TF over, that's 1,000 TF, and then 54,000 plus 8,000 is 62,000 units, wherever those units are. Divide both sides by 1,000. I'm getting 62 is the number, right? And then since I was working with degrees Celsius, and since I was taking differences, I was okay. I didn't have to convert to Kelvin first. This would have to be degrees Celsius. There you go. Take that. Good thing to do in physics too, when you get an answer, is step back and say, hey, does that make sense? Okay. Well, see, I had two masses of water that were kind of comparable to each other. They weren't exactly identical, but they were kind of in the ballpark. One was up close to boiling, one was about room temperature. So even before I solved it, I could have said the answer should be pretty close to halfway in between. Pretty close to halfway in between, maybe about 50 degrees Celsius or so. You get 62 degrees Celsius. Yeah, I can believe that. Okay. I mean, of course, it's going to tend towards the one that's more mass, so that makes sense too. Okay. Is that working out for you guys on your paper? All right. All right, ready for the next one? All right, number 57. 50-gram sample of zinc, which has, ooh, look at that. It's a small heat capacity like the previous mystery metal we were talking about. It's pretty close to that. 0.39 joules per gram Kelvin, less than a tenth of that of water. At 75 degrees Celsius, it's placed in a container of 800 grams of water, which is that. Okay. What is the final temperature of the water and the zinc together? Okay, so this sounds pretty well in line with the last couple of questions. Energy import, energy export. Hey, yeah, see if you guys can stay a step ahead of me on this one. See if you can stay a step ahead of me. If you followed what we've just been doing, then I think you should be able to. So, walk you guys through it. Get me to the answer though. Okay. I'm going to say the energy that's been lost by the zinc is exactly picked up by the water. So there's conservation of energy for thermal energy exchange. Now the zinc is going to be mass of zinc, specific heat capacity of zinc, times change in temperature of the zinc. It says what's the final temperature, so we're like calling for a TF. Okay. That's equal to negative mass of water, specific heat capacity of water, and change in temperature of the water. So that's T final of the water, which is T final we're solving for. Because equilibrium, they're going to reach equilibrium. Minus the initial temperature of the water. So here, little picture here, beaker water, zinc. The zinc is losing heat energy to the water. The water is exactly picking up that heat energy, and they're going to stop that heat exchange when they reach the same temperature. And we're solving for that temperature. All right, so I got 50 grams of zinc. Specific heat capacity of 0.39 joules per gram Kelvin. We're solving for a temperature final, and this got started at a pretty hot 75 degrees Celsius. Okay. Again, not going to worry about converting to Kelvin because I'm taking temperature differences, so it's all going to work out in the end. Okay. Mass of water is, I've got 800 grams. It's still got a negative sign. Okay. Track stuff, right? Specific heat capacity of water, I know is 4.18 joules per gram Kelvin. Number we used a bit yesterday and today so far. Okay. T final we're solving for. And the initial temperature of the water was 10 degrees Celsius. So it looks like we pulled something out of the fridge. It's on the cool side. Degrees Celsius, like that. Okay. All right. Let's go back. I should have said to you before I go plug it and chugging. Okay. We got a lot of water which has a really stable temperature, and a little bit of metal, which sure started out hot, but remember, small heat capacities for metals. I'm going to guess that the final answer is going to be probably not a whole lot more than 10 degrees Celsius. I mean, it's going to be more than 10 degrees Celsius, but not crazy much more. Okay. So with that in mind, let's solve this thing. 50 here again, distribute. That's 0.39. Okay. There's that. So 19.5 TF minus 1462 is equal to negative 3344 TF plus 33,440 units, right? But whatever these crazy units are. So I'm dropping the units just to make the math a little cleaner. Okay. Add this over. So 3363.5 TF, and this is just algebra at this point, is equal to, add this over, okay. And finally divide this coefficient. Okay. Remember what I'm looking for. Like if I get probably between 10 and 15 degrees Celsius, that's kind of what I'm expecting. More than 10, but not crazy much more. So what is that number there? 34902.5 divided by this coefficient, 63.5, and 10.38 degrees Celsius. Yeah, that's within that window. That's about what I was looking for. I said the temperature should overall rise, but not a whole lot. Temperature of the water is really stable, and also there's more mass of water compared to the metal. So for both those reasons. Okay. All right. You guys getting a number that matches an answer for us on your paper? All right, it's working out for you guys. Okay. Number 64. How much heat is needed to turn 11 grams of ice at negative 10 degrees Celsius into steam at 120 degrees Celsius? Okay, we're about to go on a 5-part journey, which matches this graph right here. So negative 10 degrees Celsius ice, that's like down here. Well, first we got to bring the ice up to the point where it's going to melt. Then we have to melt the entire ice cube. Then we have to bring the water, now liquid water, all the way up to a boil. Then we have to boil it all away. Then we have to keep heating that steam. That's a 5-part journey. You guys see that? It's gonna be a 5-part journey. Matches this picture right here. Okay. So let's break out a good amount of paper. 64. Okay, so first part is to bring the ice up to the part where it can melt. So delta Q, here, I'll say ice because we're on the ice part. Okay, so go ice, melt, water, boil, steam. That'll be our 5 parts. So the ice, that's mass of the ice. I mean, it's going to be the same 11 grams over and over. So that's just mass, right? Okay. Times specific heat capacity of the ice, which is different than water. But I gave you guys all 5 numbers that you need right here. Okay, so you guys see these 5 numbers? We're going to use all 5 of those numbers for this journey. Times the change in temperature of the ice. Okay, MC delta T. Okay. So that's I have 11 grams. You guys probably have something different. Okay. Now the specific heat capacity of ice is the same for everybody. It's 2.09 joules per gram Kelvin. You guys see that number? 2.09 joules per gram Kelvin? It's right there. 2.09 joules per gram Kelvin. And the change in temperature of the ice, well, if we need to bring it up to 0 degrees Celsius to make it start melting, and it was at negative 10 degrees Celsius, guys, what's the change? 10, right? 10 degrees Celsius? If you want an extra detail in here, I'll say 0 minus negative 10. Isn't it 0 minus negative 10? Also 10 degrees Celsius, right? Since it's a change, you don't have to convert to Kelvin because it's also 10 Kelvin. It's the same thing. Okay. So let's see how much energy is that. It's 11 times 2.09 times 10. Okay. I'm getting 229.9 joules of energy just to bring it up to the point where it's about to melt. Now that is the first part of a 5-leg journey, right? That's how much energy you have to put into that ice cube just to bring it up to the point where it starts to melt. Okay. When it starts to melt, now we're on the next part of the graph. We're on this flat line right here. Great. So how much energy does it take to melt, like fully melt the entire ice cube, turn it completely into water? Well, that is called heat of fusion. So delta Q equals M times delta H fusion. Okay. So I'm still taking 11 grams because it's the same mass. So got that. Okay. But the delta H is 334 joules per gram. You can think of that like the length of this leg right here. Okay. 334 joules per gram. That's always true for ice, water. That's always going to be true. So I'm getting 3674 joules to melt the entire ice cube. Okay. Okay. Now we have a puddle of very cold water. It's still 0 degrees Celsius, but it's on the liquid side of that lake, right? Right? Okay. So there's part 1, there's part 2, right? Now part 3 of this journey, 5-part journey, is going to be to bring the water up to a point where it's about to boil. Okay? So we're going to go from this part of the graph to this part of the graph. Okay? And the amount of energy is how far to the right on that graph we go. Okay? Same thing as last couple days. So this is melt. Okay. Delta Q for the liquid water part. I'll say water because the liquid part, we're going to bring it from freezing to boiling. So that's MC water, delta T of the water. Still got 11 grams. C water we've used several times yesterday. Today it's 4.18 joules per gram Kelvin. I mean, it should start to look familiar right now, right? You guys used that number many times yesterday and today. Delta T, well, we're going to 100 degrees Celsius from 0 degrees Celsius. So it's a change in 100 degrees Celsius. You could also call that a change of 100 Kelvin. 11 times 4.18 times 100. That is 4598 joules. That's the third leg of the journey. All right, guys good so far? Okay. Okay, now we got 2 parts left. Now we have to, now it starts to boil, right? We got to boil away that entire 11 grams. So that is the heat of vaporization. Delta Q vapor to vaporize the entire thing is mass times delta H vaporization. So it's still 11 grams. And reason it's fourth number, 2000 in some joules per gram Kelvin, or sorry, joules per gram, I should say, joules per gram. There's no temperature change there. 2260. You guys see how this leg of the graph is much longer than this leg? So it takes more energy to boil it than it does to melt it. It's another way to think of it. So 2260 joules per gram. Grams cancels, we're going to get joules. Looking at 24,000 in some. Woo! That's a lot to boil that away. It takes a lot of energy to boil water. That's the fourth leg of the journey. Okay, now we're getting real close. So now delta Q for the steam, because we're going to continue to keep the steam until we bring it finally up to 120 degrees Celsius. So MC steam times delta T. Okay. So we've got still 11 grams of now steam. The specific heat capacity of steam is 2.01 joules per gram Kelvin. And I'm going to bring this to 120 degrees Celsius from 100 degrees Celsius, which is a change in 20 degrees Celsius. You could also call that a change of 20 Kelvin. This many joules. Boom. All right, that is the last leg of that journey. So now we got to add up how much energy each part. So we're slowly progressing to the right of this graph. A little bit, little bit, little bit, little bit, little bit. And my 5 numbers are here. I'll say the sum of the delta Q's is, and I'll just add them on my calculator screen. So to bring the ice up to the point where it started melting, that was 229.9 joules. To melt the entire ice cube was 3674 joules. To bring the water up to a boil was 4598 joules. To boil all that water away was by far the most amount of energy. That's 24,860 joules. And finally, to keep the steam was another 442 joules. That comes out to 33,804.1 joules. Okay. I wonder if I put the answer in kilojoules on paper. If I did, how many kilojoules would that be? 33.8. Let's see, is there 33? Yep, 33.8 kilojoules. Bam. Good to go. So if you followed all the steps along with me, you should see an answer on your page. Match with one of those. Okay. Are we good? $65. 10-gram lead bullet. Now, here's the specific heat capacity of lead. Talking about solid lead. Okay. It's moving at 250 meters per second, strikes a tree, and is brought to a stop. Ooh, sounds like a kinetic energy connection. If all its kinetic energy is converted into thermal energy, and furthermore, let's say it all stays in the bullet. No, it's not exactly realistic, but we're maybe like an upper boundary. Okay. What's the temperature rise of the bullet? Okay. So, yeah, realistically, this would be like an upper, because some of the energy must be converted into like pushing the tree fibers out of the right way and heating up the wood. But we're going to ignore all that and say somehow it all stays in the bullet. Okay. So 65. This reminds me kind of the waterfall. We're going to mix thermal energy and mechanical energy. With the waterfall, this potential energy goes to thermal. With the one we're doing right now, I'm going to say the change in kinetic energy all goes into thermal, right? Change in kinetic energy, it all goes into heat energy. Okay. So kinetic energy, what's the formula for kinetic energy? 1/2 mv squared. Okay. And that's going to go into MC delta T. Okay. Notice what cancels out? Yeah, the mass of the bullet. Right. So even if you had like 3 times the lead, well, it's all coming to a stop. So it's all going to proportionally rise to the same temperature. Hopefully that makes sense. Right? What about this? What would the temperature rise be if the bullet was going 3 times as fast? 3 times as fast is going to correspond to what temperature rise? Not 3 times. 9 times the temperature rise. You guys see a factor of 3 on that V is going to be 9 times the temperature rise, right? So the relationships that be able to get out of the class like this, right? You're out in the real world, working some jobs, saying what's the relationship between like this cause, this effect, these variables. Ooh, I remember like this thought process then in physics. So here, we're solving for this and we know all the other numbers. So the temperature rise is the speed of the bullet squared divided by 2 times the specific heat capacity. Now something else I remember, ooh, there's a little trick here, there's a little trick, is we're mixing mechanical and thermal energy. When we did that yesterday, we had to do joules per kilogram Kelvin because kilograms is the base SI unit. So you're gonna have to do a little conversion here. Or I'm pretty sure you are, but I'm about to find out. So let's take the speed that I gave you, that's fine. So many meters per second. This was the speed of my bullet. I'm gonna square it, then divide by 2 times something, right? Now, what do I multiply by? I gave you guys joules per gram Kelvin. You guys see joules per gram Kelvin? But that's not base SI units. The base SI units are joules per kilogram Kelvin. So if you have to multiply this by 1,000, right, to get joules per kilogram Kelvin, that's exactly what I'm going to do. 0.159 joules per gram Kelvin is the same thing as 159 joules per kilogram Kelvin, right? Because it has to be in base SI units. So you can mix thermal and mechanical energy, right? That makes sense? Otherwise, you get a completely nonsensical answer. It's off by a factor of 1,000. So it's 250 squared divided by, that's on parentheses, how about that? 2 by 159. Okay, now that's a huge temperature rise, but I can believe it. We're talking about bullets. Right. So look at 197 degrees Celsius. You can also call that 197 Kelvin because we're talking about a temperature change. Okay. Whatever its initial temperature was, you add this to it to get its final temperature. All right, make sense? You guys good there? Let's do the very last one on this page, and then we'll probably cover. Because the last one deals with entropy. We haven't done the equation with yet. You do 0.05 joules of work in a coffee cup every time you stir it. So you're stirring this coffee cup. Right. What's the increase in entropy? 125 milliliters of coffee at 65 degrees Celsius when you stir it 20 times. The formula for increase in entropy, that's delta F, the increase in entropy, is the change in work or heat energy divided by the temperature that it happens at. And that has to be an absolute temperature in Kelvin. So we're doing 20 stirs. So I'm stirring it 20 times. Each stir, I'm doing 0.050 joules of work. And this all happens at, I know it says 65 degrees Celsius, but don't you have to add 273 because we're talking about an absolute temperature? Has to be in Kelvin, right? Has to be in Kelvin because we're dividing a temperature. So that many stirs times that much work per stir, kind of dimensional analysis thing, divided by this temperature Kelvin. That's joules per Kelvin. So maybe 0.003. Yeah, I see an answer that matches that, so I'm good with that. There you go. Okay, you guys good there? Tell you what, throw this in the grade tray and I'll give you guys points for what we did, and that'd be good. All right, so when you finish that, throw that in the grade tray, as long as you did the ones that we did in class. Okay. If you maybe like weren't here yesterday and you missed the ones yesterday, you can just knock this out over the weekend and turn that in Monday.